Welcome to the Deep Dive, where we take fascinating topics and explore what really matters.
Great to be here.
Today, we're heading out into space, looking at some genuinely strange stuff happening with stars.
Yeah, signals that make you scratch your head.
Think about NASA's Kepler mission. Amazing project between, 2009 and 2018?
That's right, 9 years.
It just stared at one patch of sky, watching about 500,000 stars.
And the results were incredible. Over 2,500 confirmed exoplanets from that one mission alone.
That's a serious haul, isn't it?
Absolutely. And among those were some, well, pretty extreme characters, these hot Jupiters.
Yes, the planets practically skimming their stars.
Exactly. Some orbiting in just 3 or 4 Earth days, even less sometimes.
Which sounds, frankly, uncomfortable.
And ultimately fatal for the planet. They face a pretty dramatic end.
Right, they get slowly pulled in, don't they? Can you unpack that a bit?
Sure. Because they're so incredibly close, the star's gravity exerts these huge tidal forces. It's like a constant stretching and squeezing.
A cosmic tug of war.
Precisely. And the star inevitably wins. The planet loses orbital energy, spirals inwards, until it gets too close and starts breaking apart, disintegrating, sometimes completely swallowed by the star.
Leaving behind just gas and dust.
Yeah, a sort of stellar indigestion. We think we've even seen this starting to happen. Kepler 1520.
That's the one. Tell us about that.
Well, Kepler 1520 showed these repeated dips in brightness, sort of like transits, but happening incredibly often every 15.7 hours.
Oh, that's fast.
Super fast. And the dips weren't always the same depth. That suggested it wasn't a solid planet transiting, but maybe a cloud of debris constantly changing, being stripped off a disintegrating rocky world.
Okay, so that's weird, but it kind of fits into models of planetary evolution, or maybe de-evolution in this case.
Right, it's extreme, but understandable physics.
But then there's KIC 8462852, Boyajian star.
Ah, yes. Tabby star. That one's different.
And it wasn't found by the usual computer algorithms hunting for regular dips, was it?
No, it took the Planet Hunters citizen science project. Actual people looking at the light curves noticed something deeply strange.
What did they see?
Not the nice U-shaped regular dips of a planet. Instead, these huge, messy, irregular drops in brightness.
How huge?
Up to 20% dimming, which is enormous for a star. And these events lasted for days, weeks, even months, like 5 to 80 days.
With no clear pattern.
None whatsoever, just completely erratic. It was, and honestly still is, baffling.
And when you get something that weird, the speculation starts, right? I remember hearing all sorts, swarms of comments.
That was an early idea, yeah. Or maybe a planet broke up or a moon got destroyed, leaving debris.
And then there was the, let's say, more out there idea.
Yeah.
Alien megastructures.
That definitely grabbed headlines. Wright and colleagues floated it in 2016, partly because the natural explanations didn't quite fit perfectly. It certainly got the SETI folks interested.
But the focus quickly shifted back to finding, well, more mundane explanations, or at least finding other stars doing similar things.
Exactly. Was Boyajian star unique? Or just the first example of a whole class of weird stars we hadn't noticed before?
And that's really our mission for this deep dive, isn't it? Exploring that search for other Boyajian star-like objects and what we're learning.
Precisely. What does the latest data tell us about these cosmic oddballs?
So for years, Boyajian star was this standout mystery, just one data point, which must make figuring things out incredibly tough.
It really does. You don't know if you're looking at a freak occurrence or, the tip of an iceberg.
It's hard to build a theory on a single example.
Exactly. That's why the work of people like Michael Schmidt has been so vital. Starting around 2016, he began digging through huge archives of star brightness data.
From surveys like the Northern Sky Variability Survey and ASAS-SN.
Yep, those big automated surveys that monitor millions of stars over time. He was specifically hunting for stars, showing those weird, irregular dippers, as he called them.
He came up with categories, right? Slow dippers and rapid dippers.
He did. It was based on how the dips looked. Slow dippers were the ones most like Boyajian's star. The dips were relatively narrow, less than a few days long, and they didn't happen very often, maybe fewer than 3 times a year.
Okay, infrequent, shorter dips.
Right. Then rapid dippers showed dips much more frequently, like more than 8 times a year.
So more active.
Kind of, yeah. In his first big search back in 2016, he flagged 21 potential candidates.
And how many look like Boyajian's star?
15 of them fit that slow dipper profile. So 15 potential analogs.
15, that's way more than one.
It is, but Schmidt pointed out something important. His search covered a much larger volume of space and number of stars than Kepler did.
Ah, okay.
So statistically, finding 15 in his huge survey was actually pretty consistent with Kepler, with its smaller field of view, finding just the one.
Right. It didn't necessarily mean they were common, just that maybe Boyajian star wasn't a complete unicorn.
Exactly. It suggested there might be others out there, even if they're rare.
And Schmidt kept looking, didn't he?
He did. Published more work in 2022, expanding the search.
Find any more?
Yep, another 15 slow dipper candidates turned up. So now we had a growing list, maybe 30 stars that seemed to show this strange Boyajian-like behavior.
Okay, having more examples is key. But just knowing they dip isn't enough, right? You need to know what kind of stars they are.
Absolutely crucial. And that's where another space mission became incredibly important, Gaia.
Ah, Gaia, the star mapper extraordinaire.
Couldn't have put it better myself. Gaia's job is to measure the positions, distances, and movements of billions of stars with unbelievable precision.
Using parallax, right. Measuring the tiny shift in a star's apparent position as Earth orbits the sun.
Exactly. Gaia's measurements, especially from its early data release 3, gave Schmidt really accurate distances to his dipper candidates.
And distance is the key to knowing a star's true brightness, its luminosity.
Precisely. Once you know the distance and how bright it appears, you know how luminous it really is.
So, what happened when Schmidt took these dipper candidates, now with known luminosities thanks to Gaia, and plotted them? Where did they land on that fundamental stellar map, the Hertzsprung-Russell diagram?
That's where it got really interesting. They weren't just scattered all over the HR diagram.
No, they clustered.
They did. His 2022 analysis showed they fell into a surprisingly restricted area.
What kind of stars are in that area?
Two main groups, actually. One cluster was around main sequence stars, like our sun, roughly 1 solar mass.
Yeah, sun-like stars.
And the other group was near the red giant branch, specifically around the evolutionary path expected for stars that started out around twice the mass of our sun.
So sun-like stars and stars evolving into red giants.
Exactly. And crucially, those main sequence, sun-like dippers, are considered the best candidates for being true analogs to Boyajian's star, which is also a main sequence star.
So the weird dipping isn't happening randomly to any old star. It seems to be linked to specific types or maybe specific stages in a star's life.
That's the strong implication. Finding more dippers was one thing, but finding they shared common stellar properties was a big step.
And did the statistics back this up? Was this clustering on the HR diagram significant?
Yes. Schmidt's analysis showed it was statistically significant. They were much more clustered than you'd expect if you just picked random stars.
Which really strengthens the idea that these dippers are a related group, maybe experiencing the same underlying phenomenon, whatever that is.
Exactly. It suggests we're genuinely identifying a distinct population of stars linked by this strange dimming behavior.
Okay, so they share stellar properties. What about where they are in space? Are they spread out all over the sky, or is there something going on there too?
No, this is where it gets perhaps even more intriguing. Schmidt's 2022 paper pointed out something striking about their distribution on the sky. There seemed to be an apparent clump.
A clump of dipper stars.
Yeah, 12 of the dipper candidates appeared grouped together in a specific patch of the sky, roughly between 254 and 303 degrees in right ascension, if you want the coordinates.
Like a little cosmic neighborhood of weird stars.
Kind of seemed that way. And importantly, Boyajian's star itself lies within the same region of the sky.
Whoa. Okay, that feels significant.
It definitely caught the eye, especially because the density of similar dipper candidates seemed much lower elsewhere in the sky.
Could it just be because that part of the sky is crowded? Like looking through the Milky Way's plane?
Good question. Schmidt checked for that. The higher density of stars in the galactic plane didn't seem to fully explain this apparent concentration.
Okay, so it might be a real grouping. And Gaia gives us the distances too, so we can check if they're actually close in 3D space, not just projected onto the same bit of sky.
Precisely. We know Boyajian star's distance very accurately now, thanks to Gaia DR3. It's about 444 parsecs, or roughly 450 light years away, plus or minus just a couple of parsecs.
Super precise. So what about the other 12 in that clump? How far away are they?
Using the Gaia parallaxes for all of them, Schmidt could map them out in 3D.
Was it a nice tight ball of stars?
Well, it got a little more complex. First, 4 of the 12 turned out to be much, much further away, over 1,000 parsecs, more than double Boyajian star's distance.
Okay, so maybe not part of the immediate group. What about the other 8?
The remaining 8, plus Boyajian's star itself, so 9 stars in total, did seem to occupy a common volume of space. But it wasn't a sphere.
No. What shape was it?
It was elongated, stretched out, about 50% longer in one direction compared to the other two.
Huh. An elongated structure of these unusual stars. Could that just be uncertainty in the distance measurements?
That's another good question. But the Gaia parallax uncertainties are tiny, less than 0.8% for these stars. Schmidt argued that measurement error couldn't account for this elongated shape.
So a potentially real, stretched out group of stars that all exhibit this weird, irregular dimming.
That appears to be the case.
Okay, an elongated structure that really gets you thinking. And this led Schmidt to speculate a bit, didn't it? Gently floating some less conventional ideas.
He did, very cautiously. Given that we still lack a slam-dunk natural explanation for Boyajian's star, he sort of opened a crack to the idea of interstellar travel. He basically said, look, if advanced civilizations can travel between stars and colonize, you might expect to find clusters of inhabited systems in certain regions.
Right, like a settled area of the galaxy.
Potentially. So he suggested that perhaps this clump of dippers and maybe other stars nearby could be interesting targets for SETI searches, the search for extraterrestrial intelligence.
Wow, okay. Just to be clear, he wasn't saying it's aliens, but more like this grouping is weird, the dimming is weird, maybe he said he should take a closer look here.
That's exactly the gist. It's a suggestion based on an unexplained observation and a theoretical possibility. Very speculative, but thought-provoking.
Absolutely thought-provoking. Spatial clump of stars doing weird things. But even putting the SETI angle aside for a moment, just finding more dippers, seeing they have common properties, and maybe even a spatial connection, that's real progress, right?
Huge progress. It moves Boyajian's star from being a total anomaly to potentially the prototype for a whole class of objects we can now study systematically.
Are there other big efforts underway to find more of these oddballs or other kinds of weird transient events?
Definitely. The Virasi-Rubin Observatory is the big one everyone's waiting for. It's set to start its main survey in late 2024.
Formerly the LSST.
That's the one. It will survey the entire southern sky repeatedly, generating an unprecedented amount of data. It's bound to turn up all sorts of rare, transient, and just plain weird phenomena. We'll likely find many more dippers, maybe even stranger things.
And people are developing smarter ways to sift through all that data.
Constantly. New algorithms are key. For instance, Chakraborty and colleagues in 2022 developed a very flexible method to find periodic signals without assuming they look like simple planet transits.
Did they test it on existing data, like from tests?
They did, on a huge chunk of test data. They found hundreds of new periodic signals, which is great. But interestingly, none of them looked quite like Boyajian's star's unique, irregular pattern.
So maybe missions like Kepler and TESS, designed primarily for regular transits, are inherently less likely to flag these really irregular dippers compared to the broader all-sky surveys Schmidt used.
That's a really interesting point. It could be an observational bias. The way you look influences what you find.
Makes sense. What about looking for things that don't just dim, but maybe vanish altogether? Or appear out of nowhere?
Another fascinating area, there's the VESCO project, Vanishing and Appearing Sources During a Century of Observations.
Patchy name.
Isn't it? Led by Beatrice Villarreal and her team. They compare old photographic sky survey plates with modern digital surveys, looking for objects that have disappeared or suddenly popped into existence.
Searching for extreme transients, maybe even things that aren't, well, natural.
That's one of the possibilities they keep open, alongside finding rare astrophysical events. They've already found some really puzzling candidates.
It's like that cluster of things on the old Palomar plate from 1950.
Exactly. 9 transient sources, all clustered together on one plate from 1950 that just aren't there on earlier plates, later plates, or even in deep modern surveys.
What could cause that?
Still debated. Could be plate defects, weird reflections, or something genuinely astrophysical and very brief. Or, something else entirely. It highlights how many unknowns are still lurking in the data archives.
It really does. So it feels like this whole field searching for unusual light curves, for transients, for the truly weird, is really just getting started in some ways.
I think that's fair to say. And missions like Gaia are providing the fundamental context, the distances, the properties of the stars that lets us start making sense of these oddities.
You mentioned Gaia might even help in the search for Dyson spheres, which maybe we can talk about next time.
That's the plan. Gaia's data is proving incredibly versatile for tackling these big, challenging questions about what's out there.
So wrapping this up, Boyajian's star is still this captivating puzzle. But it's not quite the lonely enigma it once seemed.
Right. The search is on, we're finding more candidates, and Gaia is helping us see potential connections between them.
And it leaves you with that big question, doesn't it? Are these dips and fluctuations just, weird natural processes we don't understand yet? Dust clouds, stellar activity,
Which is still the most likely explanation for most, if not all of them.
or could some tiny fraction of them be hinting at something more complex, maybe even artificial? That clump of dippers really makes you pause and think.
It does. It reminds us to keep an open mind while rigorously pursuing the natural explanations first. Future observations, especially with more powerful telescopes, will be key.
Absolutely. If you listening want to dive deeper yourself, definitely look up Boyajian star, the Kepler mission's legacy, and maybe check out the Planet Hunters or Vasco projects. It's a fascinating ongoing story.
The universe keeps throwing curveballs, doesn't it?
It certainly does. And you have to wonder what other surprises are waiting just over the cosmic horizon. Thanks for joining us for this deep dive.